welcome to Next Gen Scientist at the Institute of Science and Technology, Austria. My name is Ana Rita Cavaco, I am your host and I'm here to bring you the amazing science done here at ISTA and the stories of the people who do it. Today my guest is Jean-Yves Desaule. He is a postdoctoral researcher at the group of Professor Maxime Serbin and he will tell us all about becoming a theoretical quantum physicist. Hi Jean-Yves. Welcome and thank you for being here today.
Hi, well, thanks a lot for the invitation.
Now, before we dive into what a theoretical quantum physicist is and how you became one, about which I want to know everything, let's start with our quick round of 5 questions. Ready?
Ready.
So let's go. One word that you use to describe your research?
I would say puzzling is a good one.
Great. What is your brain fuel? Caffeine, snacks, memes, or just straight panic?
I would say caffeine, like most scientists probably.
Yes. What is the most unexpected place your research has taken you?
I mean, I'm a theorist, so I don't do field trip or anything exciting. I just go to conferences. But it turns out people organize conferences in some pretty interesting place. So most unexpected would probably be Vegas when I went for a conference.
That is surprising.
Yeah.
And are you a night owl or early bird?
Early bird, definitely.
Very good. And for last, complete the sentence. I never thought being a scientist would mean...
Having so many meetings, just so many of them. Like it's impressive how much time it takes, and but I guess that's how it is.
Yeah, one of those things that have to be done.
Yeah.
Very well. So before we take a look into your work, tell us a bit about what is a theoretical quantum physicist and what we are about to see.
Yeah.
So what you do.
So basically, as a quantum physicist, I study quantum systems. So that means systems which are like very small and very cold. For example, like atoms cooled close to absolute zero, where quantum mechanics really applies. And then my research is focused on simulating how these systems evolve in time and how we can kind of use them to make better memories, for example, for quantum computing.
So let's take a look, let's take a sneak peek into Jean-Yves' work and we'll be back for some questions about it.
So yeah, how I said during the interview, my research is mostly focused on fundamental physics and learning more about quantum physics itself. And in particular, I like to work with experimentalists to try and use their experiment to learn more about physics. And one of the experiments I really like is Rydberg atoms. Because it's very simple. It's just atoms held in place by lasers, and these atoms can be at rest, so with no energy in the ground state, which I would just denote by a circle, or they can be excited. So we just give them more energy, which I denote with this field circle, and they can oscillate between the two states, and we can control that with the lasers. So it's a very simple system, and experimentalists are able to really control where they place them. So you can do something like you place them on a ring, and then what we want to see is if we prepare special configuration, what happens to them. And notably, what we're interested in is equilibration. So one thing you can look at is, for example, the density of excitation. And the problem with quantum mechanics is that everything seems to equilibrate. So if I look at this quantity over time, whether I start from a low value or a high value, it will generally all go to the same at late time. And that's kind of a problem, because if now I just give you the data from this time and ask you, oh, what was the original value of this? You won't be able to tell me. You would need infinite measurement precision, which of course is not realistic. And that's kind of a problem for any kind of quantum memory, for quantum computers, because we really want to be able to save this information in some way. And so what we would want is to find some state or some system where instead of going to the same value, it either stays at some fixed value, then we don't lose the information, or it kind of goes away, but then it comes back. And so at special times, we know the information. So let's look first at a small system that I can do analytically, that I can use to benchmark things on the computer, and then go to larger system. So what do we do? Well, first we look at how the system is, because these Rydberg atoms have a very special properties, is that if you take two of them together, they can both be in the ground state. You can have one in the ground state, one in the excited state, or you can have two of them in the excited state. No, you cannot have that. This is forbidden because it costs too much energy at the system. Because these atoms are cooled very low, and so very high energy intensive configuration, they just cannot be created. And so these systems are nice because they have this kind of constraint, these weird things, and we will see that it leads to some strange behavior. So now that we know that we have this, we have to see what we can do with a small system. So let's start with, let's say, 4 atoms. And the first thing is we have to check all the configuration that the system can take, knowing this constraint. So you can have no excitation at all, that's always permitted. You can put 1 excitation, and these are all the configuration that we are allowed with this rule. And the next thing we need to characterize the system is kind of how these all interact together. As we said, these atoms, they like to change state, go from excited to ground state. So if I'm here, one of them can say, okay, I want to get excited. We can do that with a laser. So we can excite the first one, second one, or any of there. Or we can excite even more of them from here to here. And this is kind of a graph representation which shows all the state that we can have and how we can move from one state to the other. And once we have this, we can put it in equation and do a lot of linear algebra, and then we can basically compute anything about the system. For example, if we start in this state with no excitation, we can compute the state of the system at subsequent time. And you might imagine this is, oh, at some time it will go to this, and then it will go to this. But actually, since it's quantum mechanics, it will not do that. It will be in a superposition of all the states in the system. And so even for that simple system, just writing down the state at late time would take maybe that of the board in length. So it's very tedious. So let's stick to the easier quantities. So this number of excitation, this density of excitation. And if I solve the system, I can find that over time, if I start from there, and in itself, for such a small system, it's not very useful, but it will be crucial because we can use it to benchmark it, what we do on the computer, and be sure that it's correct before scaling it up. Okay, now that we've derived things analytically and know what to expect, we can go to the numerics. So I've coded things because it takes a long time, but we can run it in real time. So we indeed, for 4 sites, we find 7 configurations. And we can check, and these are indeed the same, right? A 1 is an excited state, and a 0 is a ground state. And finally, we can check that the graph representation, so how the system interacts, is also the same. And now we can solve it in real time. Done, took a fraction of a second. We put the analytical formula and we compare them. And you see that the red and the black basically overlap perfectly. And to be quite sure, we can look at the difference. This is what we get. This is scientific notation, but basically what this means is that the 2 data sets agree up to the 14th decimal, which is almost as good as you can get with a computer. So yeah, things seem to work quite well. Then we can go to a larger system, and now we go with 12 sites, and we find 322 configurations, so solving that by hand would take you probably months just because of the sheer number of things you need to keep track of. But the computer can solve it, again, fraction of a second, so that's nice. And we can plot the density of excitation over time. And now we plot it for 2 states. One is a state with no excitation, as before, where you have a bit of oscillation, but they damp quite rapidly. And the other one is the state with the maximum number of occupation, so every other site is excited, which has much cleaner oscillations. And that's something that's very weird that we don't expect. We expect this to go to the same value. And what is nice with this simulation is also that it's let us access things that you cannot access in experiment. For example, we can really track the state of the system at all times, not just quantity like this, and that can tell us a lot about what is happening. So what can we do? Well, we can do the same graph representation as before. So now it's a lot more packed, right? So as before, every point is just a possible configuration. And as you go to the right, you have more excitation. And as you go up, the excitation are more on the odd sides. And what we can plot on this is how much of the state is localized on every of this configuration. So yellow is very strong localization, and black, it means the system does not occupy any of this configuration. And what we would expect if things were equilibrating and we would lose information kind of, is to see something like this, something very homogeneous, where there is no special point in the system where the information is, it's just spread everywhere and we cannot recover anything. And now we can look at what actually happens when we start from this specific state here. And as we let it evolve, we see that instead of spreading everywhere evenly, we always have kind of a small part of the system which is occupied, so a small number of configurations which are occupied, and the rest of the system is in black, meaning it's not being explored. And that's essentially an effect of quantum interference that we do not get classically and which lead to this beautiful oscillation in N.
So, welcome back. I am curious about several things that you showed us. So, your work is, of course, very important to advance quantum computing. So, what can quantum computing be used for?
So, the biggest hope for quantum computing are things like discovering new drugs. So trying to better being able to understand how proteins fold, because these obey quantum rules and that's super hard to simulate classically. So with a quantum computer, we would be able to do much more research on this. So new drug discovery is probably the best application that we have in mind.
And so when you say that it can help to understand how a protein folds, it's about how a protein takes its final shape, right?
Yes, exactly. And this final shape has a lot of influence on how it will act with other things. And for example, for new drugs, if you take the same protein and it can fold different ways, it can have very different effects. So understanding this shape is very, very important.
So it can be used for many, many different things, actually, from biology to pharmacology to
exactly.
engineering. Yes. And from the beginning, you talk about like ground state, excited state. So what do you mean by this? What is this ground state, excited state?
So it basically tells us about how much energy a particular atom is. So you can think of an atom kind of a small solar system where you have the nucleus with electron orbiting around. And if you give it energy, the electron can orbit further away. And basically the ground state would be where the electron is the closest to the nucleus, and as you go to excited state, it goes further and further away.
Okay.
So that's very simplified picture, let's say.
Yes, of course. That's very cool. So I'm also curious about this because you showed us some calculations that you did by hand, but in your daily life, as a theoretical quantum physicist, do you also actually do your math by hand until some point?
Well, usually yes, as I showed. So first of all, to check what I do with the computer, because it's super easy to have a bug in the code, and you really don't want that. You want to check everything, at least in the simple case. And we still do also a lot of analytics when we want to try to do some kind of approximation. The problem is very complex, but we can kind of take some assumption which allow us to solve it analytically and have actually like something we can see, like some expression for it and not just numbers on the computer.
Okay, so when you say analytically,
it's really just pen and paper,
okay,
like I did on the board.
Yes, very well. And just a little follow-up on the math part. You mentioned some terms like linear algebra. What is exactly this?
Okay, yeah, so linear algebra is basically, in, let's say, the big picture, that you don't deal with one big complicated equation that is super hard to solve, but you have many simpler, at least usually, equations that are linked to each other. And you really need to solve all of these together. They all depend on each other. So the difficulty comes from the fact we have so many of these equations, even if one by one they look simple.
Thanks a lot. We've got to see the big picture about what you do in your work as a theoretical quantum physicist. And in fact, this is a special year for your area. So this is the International Year of Quantum Science and Technology. So tell us, why is quantum physics important?
Well, so first of all, I would say quantum physics has already done quite a lot that people maybe don't realize. Because if you look at technology we use these days, it's a lot of a semiconductor transistor. So what we have in our computers, basically the building blocks require understand quantum physics first. And so it's hard to overstate how much this has changed the world, right? Just computing, which requires quantum physics, and other important technology like lasers, for example, you need to understand quantum physics to really understand it. So I'd say just because of this, it's already had an immense impact. And then with quantum computing, people hope what they call like the second quantum revolution, where if we have quantum computing, we will be able to do a lot with it. For example, this drug discovery and solving other hard problems that we cannot really do with, let's say, classical computers.
Okay. So indeed, it has many different applications.
Yes.
So to become the scientist you are today, you, of course, had to become an expert in quantum physics. But when did you realize you wanted to be a physicist?
Well, actually, somewhat late. I would say I always knew I kind of wanted to be a scientist already when I was, let's say, rather young. I was always interested in. But I hesitated. I didn't know if I wanted to do math, chemistry, physics. And I kind of chose physics as a middle way because math was a bit too abstract. Chemistry seems a bit too applied, and physics just seems to be like in the middle. So that's kind of how it went.
I think that's a very interesting way to put it. So it comes from your love for science in general.
Yeah.
So to have this profession you have today, what did you study? Walk us through the path that you did.
Well, so already from, let's say, secondary school, I was doing like the science major, same in high school. And then I went to university in Lausanne at EPFL, so in Switzerland, because I'm from Switzerland. And there, that's the point where I had to really choose between this chemistry, math, and physics, and I chose physics, and turned out I liked it quite a lot. So I did then a master's in physics with a specialization in theoretical and numerical physics. And after that, I was looking at PhD, and quantum physics seemed to me like the most kind of interesting, the most intriguing and puzzling. And I ended up doing my PhD at the University of Leeds in the United Kingdom, looking at these quantum systems.
So by the end of your master's, it was already natural to you that you wanted to continue in academia?
I would say yes. I was really enjoying research during my master's, and I was like, yeah, this is something I can see myself doing more of. And I went for the PhD, and I really liked it. So yeah, I'm very happy to still be in academia doing research.
That's really cool. And this also takes us to our next question. So on the way to become a scientist, sometimes the road is a bit rocky. What would you say that was the biggest challenge that you faced to be where you are today?
Well, I would say I'm quite lucky and quite privileged, so I don't think I had any, like, let's say, external barrier that kind of made it much harder for me. So in that regard, I'm pretty lucky. I would say the biggest difficulty was doing like good enough research to still be, let's say, in line for postdoc and everything in academia. Let's say be competitive, because it's still very competitive to get good positions. And in that particular case, I mean, I do theory and numerics, and the biggest challenge was basically trying to extract any meaning from the heap of numerical data that we produce, which is maybe a bit specific, but I'd say that that's what applies in my case.
Yes, sometimes, I mean, not sometimes, all the times, the more we stay in academia, the more specific our work turns. But
Yeah.
it also means that we will have our niche.
Yes.
That's very interesting. And on the other side of this, what motivates you the most? What gives you the most energy about your work?
Well, honestly, it's not even the goal at the end. It's more like what I do on a day-to-day basis. Because if you look at, let's say, my work, it seems like a very big task to understand how nature works and all. But if you divide it in, let's say, small bits, they all kind of look like riddles. And it's really like motivating me. It's really stimulating for me to really solve these riddles, like every day a new riddle to solve. And I just really like it.
Yeah, and I understand from our talk that this challenge also motivated you to continue in academia, to pursue a PhD, and now to be a postdoc.
Yes,
right?
exactly, yeah.
So you intend to constantly be challenged.
Yeah, I think that's just part of research, and if you
Yes.
don't like this kind of challenge, it's probably not the best career for you, but it's something I really like, at least for the moment. So yeah, it's really what motivates me, like facing these challenges.
That's really cool and inspiring, actually. Then, what's next for you? What are your objectives for the future?
Well, I mean, career-wise, my goal would be to find a permanent position, hopefully have my own group in Europe if possible, and ideally in Switzerland where my family still lives. So I probably have a next postdoc lined up after that, and then hopefully a permanent position or something. But I'm also looking a bit at other options. So I'm going to do an internship at Planck QC, which is a private company that also does quantum computing. So I'll be able to see a bit the other side of quantum, the industry. So who knows, maybe I'll be inspired by this and do that instead. So it's still a bit open.
Yeah, that seems like a very nice opportunity because indeed scientists can do many different things.
Yeah, no, I'm really intrigued by how it works in the private sector, quantum in the private sector, so we'll see.
Yeah, that's super cool. Now I would like to finish this segment with asking if you could meet teenage Jean-Yves again, who was already so passionate about science but loved many different things, chemistry, math, physics. Which advice would you give him today?
I mean, I think I'd be happy as well doing chemistry or math, so I wouldn't try to nudge any direction. I would probably even go the other way and say that you don't need to focus so much on grades and studying, and that you should, enjoy doing other stuff outside, probably.
Yeah, it's important not to forget about our hobbies, our free time, because it also helps us then being even more focused in our work.
Yeah, definitely.
I think. Okay, thank you so much for sharing your story with us and your path into quantum physics. So now it's time for our segment, This or That. I will ask you several questions with two options, and we will see how many you can get right in 1 minute.
Okay.
So in today's episode, the theme of This or That will be Who Said It? So I will give you a sentence and the names of two personalities, and you have to guess who is the author.
Okay, well, let's see. I don't think I will fare very well, but we'll see.
Okay. So we have this stand clock to control our time, and let's see how many you can get right in 1 minute.
Okay, let's go.
Ready?
Yes.
Okay, so imagination is more important than knowledge. Albert Einstein or Taylor Swift?
Einstein.
Correct. Be humble, hungry, and the hardest worker in the room. Dwayne "The Rock" Johnson or Stephen Hawking?
The Rock.
Correct.
100%.
Success is a lousy teacher. It seduces smart people into thinking they can't lose. Kanye West or Bill Gates?
West.
Wrong! I don't want other people to decide who I am. I want to decide it for myself. Marie Curie or Emma Watson?
Marie Curie.
Wrong! I have
hard.
not failed. I've just found 10,000 ways that won't work. Jennifer Lawrence or Thomas Edison?
Edison.
Correct. The good thing about science is that it's true whether or not you believe in it. Kim Kardashian or Neil deGrasse Tyson?
Neil deGrasse Tyson.
Correct.
This one was a
Nothing
bit easier.
nothing in life is to be feared, only to be understood. Olivia Rodrigo or Marie Curie?
Marie Curie this
Correct. The universe is under no obligation to make sense to you. Billie Eilish or Neil deGrasse Tyson?
Neil deGrasse Tyson again.
Correct.
And I think the time has run out, sadly.
Oh, okay.
I think I cheated the last one, but with the time. But let's count it.
I think you have a pretty good score.
Yeah, I did better than I thought I would, to be honest. Some of these are pretty hard.
Some of them were a bit tricky,
Yes.
I have to confess. So, thank you once again. Thank you very much for coming here today and for taking this challenge and sharing with all of us how you became a theoretical quantum physicist. So, I have a gift for you. It's a Vista notebook where you can take notes about, you can do the math that you do by hand, you can
Perfect.
do it there.
Always need notebooks. That's a great addition. Thanks a lot, and thanks a lot for the invitation. I'm very glad to be here and to be able to kind of share what scientists do and how one becomes a scientist.
Thank you very much.
Thank you.
And to our viewers, thank you for joining us today. We would love to hear your thoughts and questions, so don't forget to leave them in the comment section. And if you liked what you saw, share it, subscribe to our channel, and bring a friend next time. And I will be here to bring you the amazing science done here at ISTA, one awesome guest at a time.